The first speaker is Sebastian Gomez. Sebastian got his PhD at Harvard, then he did postdocs at Space Telescope, and where's your other postdoc?
Also Harvard.
Yeah, also Harvard.
Yes.
Okay, and today he is going to be talking to us about finding exotic transients in the era of big data. I'm going to switch.
Yes, there you go. Okay. Oh, thank you for having me. Thanks, Stella, for the invitation. I am Sebastian Gomez. I'm a new faculty member at the Astronomy department here at UT. And also, this is the first talk I give with the logo of my research group, which is the University of Texas Transient Explosions. We're working on everything exploding star related. So to give you a little background of what I do, there's telescopes all around the world that are scanning the sky all the time, right? They're on Earth and in space, and they're taking pictures every few nights, looking for changes. This is everything from like the Zwicky Transient Facility, Pan-STARRS, TESS, Atlas, Gaia. You're an astronomer and you know these. But what this gives us is that every now and then, when you revisit a certain place in the sky, you will find a new source. So in this case, this was a before and after, and you see nothing here. And then a few days later, you take a picture of the same part of the sky and you find the new source, right? And that is the main principle of time domain astronomy. It's just changing universe and looking for changes in the universe, right? And those new sources that appear in the sky can be one of many things, right? It can be exploding stars, supernovae. It can be a black hole falling into a black hole, getting torn apart and producing a bright flare. It can be two stars crashing into each other. It can be just one temperamental star spewing out material, among many other things. And if you look at the night sky and you just plot on where these objects happen, this is a picture I took in Chile and plotted the actual locations of explosions within a year. And you see the sky is full of them. Like it's happening all the time. This is not a rare event. And here I have classified them as type 1, type 2, and unclassified. I'll tell you what that means. But in general, what I want you to take away from this picture is that most of the points are white, meaning we don't know what they are. All of these discoveries happen with what we call photometry, which is just the fancy word for taking pictures and looking how the brightness of the object changes with time, right? So this is relatively cheap. All of these telescopes are taking pictures of the universe and measuring the evolution of brightness of these explosions. You see the explosion happen and then fade away. But the real gold is in spectroscopy, which is when you take a spectrum of the thing that exploded to try to find out its composition, right? And this is way more expensive, right? We don't have surveys that are like scanning the whole time with spectroscopy. They are photometry, but some of them, we managed to get time to do spectroscopy, and those are the ones that we can classify. And this is the main problem that we have right now in the field of time domain astronomy. If you see, this histogram is showing you the total number of supernovae, the total number of stellar explosions as a function of year. And our photometric resources, the telescopes that are taking pictures of the sky all the time, are just exploding. We just have thousands and thousands of these discoveries. But our spectroscopic resources, the big telescopes that are doing the actual spectral classification and obtaining chemical signatures of these explosions, those are staying constant. All right. So right now, we are already in the era of big data, in that we can only really classify about 10% of all the objects we discover. And my job is to figure out in that 10%, which are the hidden gems, which are the stellar explosions that are going to inform physics, which are going to tell us about the universe, right? Here. Right now, I only have time to tell you about one of my favorite type of stellar explosion. This is my main subject of study called superluminous supernovae. Like their name implies, superluminous supernovae are very luminous supernovae. A regular supernova, a stellar explosion, happens when the core of the star collapses, and they are powered by radioactive decay. So a star explodes, it produces a bunch of nickel. That nickel decays into cobalt, and in the process, ejects photons. That's a normal supernova. And it has, at most, a solar mass of nickel. That is the most you could conceivably see in a regular stellar explosion. So you say, okay, superluminous supernovae are the same thing, just with more nickel, all right? That does not work, all right? Because first of all, in order to reach the luminosities, these objects are 100 times brighter than a normal supernova. And in order to reach that luminosity, you would need about 35 solar masses of nickel, which is, first of all, insane. And more than that, the amount of cobalt you would expect to see at late times is only less than 0.3 solar masses. So you're saying, okay, these objects are not a normal type of supernova. They are not produced by the same radioactive decay process that we're familiar with. So there has to be something else that is making them so bright. The leading hypothesis is that it's a magnetar central engine. So this is a highly magnetized spinning neutron star that is at the center of the explosion. And it is this highly energetic neutron star that's heating up the material, producing this extra luminosity. And with this model, we managed to reproduce the peak brightnesses that are observed. The spectroscopic features are replicated, and the late time evolution all seems to match. So it seems that this is the right direction, but there's still many unanswered questions that we have about superluminous supernovae, like how do they relate to the environments? How do they relate to other types of supernovae? What their diversity can look like. Like we just discovered one last week that looks like unlike any other we've ever seen. So we're still learning things about it. And the problem is, again, data, right? So we're taking pictures of the sky and discovering all of these transients, but superluminous supernovae make only about 1.5% of all transients we find. So if you just have a survey that is finding things randomly in the sky and then you spectroscopically want to classify things randomly, only about 1.5% of those would be superluminous supernovae, which is not a very efficient way of starting with. What about if we could turn that into, say, 85%, right? Because we are limited by telescope time. We want to make the best use possible of our limited resources. So if we could target the observables of these supernovae, like we can see their brightness, we can see how they're evolved, we can characterize where they're coming from, their host galaxies, and use machine learning to make all of this process more efficient. And that's exactly what I did. I wrote this machine learning algorithm called Fleet. It is public, it's on GitHub, it's been working for a few years. I'm going to go through all of these steps, but in summary, it queries supernovae or explosions that happen, it obtains properties of the host galaxy, fits the light curve with a certain model, and then runs this data through a random forest algorithm to predict which ones are most likely to be superluminous supernovae or not. So, going a little slower, this is a map of all of the transients that have been discovered up to, when did I make this? January 2024. I should update it by now. But that's a map of the sky generated by the Transient Name Server. The Transient Name Server is a website where all of these transients are reported to. So Fleet will grab data from the TNS, mainly the coordinates of the object. And first, we need to figure out where it came from, right? And the first thing we do is figure out what's a galaxy and what's a star, which is sometimes easier said than done. You have this image of the sky, you know an explosion happened, and you need to associate it with a galaxy that came nearby. But you don't want to, by accident, look at a star. So in this case, I'm showing the method that we use to discern stars from galaxies, in that a Crone PSF is a way of measuring the flux of an object that is pretty elongated. You can see here, it's just encompassing all of the light from this galaxy. And a PSF magnitude is just a Gaussian that's center on the cusp of that source. And you can see the difference between something that's very elongated, the difference between the PSF and the Crone is going to be pretty large, and something that is very point-like, very star-like, the difference is going to be pretty small. And that's how we differentiate stars from galaxies. Once we have the star-galaxy separator going and working, then we can say, okay, we know these are galaxies, supernovae happen in galaxies, so let's only consider the galaxies. Which galaxy is the most likely to have hosted this supernova? Because sometimes you have a supernova right here, and there's a galaxy right here and one right there, and you're like, which one did it come from, right? For this, we use a simple equation called the probability of chance coincidence that calculates how likely is it for that galaxy to be there by chance. So the one that has the lowest probability of being there by chance is the one that is most likely to be the host galaxy of this explosion, right? And we select one of them. By experience, this method is about 96% accurate, which is pretty good. We could spend a lot more time making it slightly better. But one of the goals of Fleet is to work fast. So I do reach a compromise because I want this to work on thousands of transients. So I don't necessarily want to use the most complex and most accurate model at the expense of like doubling or tripling the rate. Yes?
How much do you worry about the host galaxy just being fainter than the detection limit?
Oh, that is part of it. So superluminous supernovae tend to be hostless. So there is a limit past which if the galaxy with the lowest probability of chance coincidence is less than 5% likely to be there by chance, then we just call that hostless. Because it is most likely that is just not associated with it, and it's actually a dim, tiny thing under the explosion that we can't see. So yes, that is very much a consideration. We measure things like the radius of the galaxy, its magnitude, and its separation to the transient. And then we also fit the light curve of the supernova with a very simple model, because again, we want this to be fast. And we determined that the most important features to determine whether or not something is a superluminous supernova is the width of the light curve. They tend to be pretty slow, so they last longer, how fast they fade, the time they take to reach peak, and the color at peak. So now we have all the information from the host galaxy, like its size, color of the supernova, the decline rate, all this, and we feed all of these features into a random forest algorithm. So a random forest algorithm, what it does is it fits what are the optimal set of questions that I can ask about a population to separate it into its purest possible classes, right? So if you have an object and you say, is this property X, say brightness less than a number 3, then go into this box. Is the separation to the galaxy C greater than the number 5, put it into this box, and then it goes in there. So when a new object comes in, you run it through the same questions, and if it falls into this group, you can say, well, all the superluminous supernovae are in that group, so most likely that is also a superluminous supernova. And this is a decision tree. It's called a random forest algorithm because you will use hundreds of trees to average out the predictions and get an actual probabilistic estimate of how likely any object is to be a superluminous supernova or something else. These were our predictions from 2019, I think, of the original paper, in which we have a measure of completeness. Completeness means out of all the superluminous supernovas we ever find, how many of them are we actually recovering, right? And this is pretty low, about 30%, but that's fine because we're finding thousands and thousands of these objects. We want to optimize the use of our telescope time. We want to maximize purity. And purity means out of every object that I observe spectroscopically, how many of those actually turn out to be superluminous supernovae, like our success rate, right? So we predicted a purity of around 50%. We ran the survey for 2 years, and these were the results. Out of the 50 superluminous supernovae that were discovered worldwide in 2 years, 21 were classified by fleet, so almost half. Our purity actually turned out to be much higher than expected, about 80%. So we were pretty successful at finding these and not accidentally observing other things. And our real world completeness limit, that should be an upper limit, not a twiddle, is around 50%. I say upper limit because we don't know about the things we didn't find. So this is just using every supernova that other people found that we didn't. That's a rough measure of completeness, but obviously it could be much lower. And that's what we ended. We compiled a sample of 260 superluminous supernovae, the largest catalog of these objects, to try to find out properties about their explosions. I'm not going to go through the details of the paper, but like this is an example of trying to, for example, measure the masses of the stars that explode, right? And we can get a pretty accurate measurement of the distribution of the mass of the progenitor star that led to those supernovae. So this is like 10 solar masses, 20, 30, 40 seems to be around the limit. But also, we were able to create a map of the average superluminous supernova, right? This general map allows us to then prepare for future missions, such as the Nancy Grace Roman Space Telescope. This is a telescope I'm heavily involved with. It's the next NASA flagship mission. It's an infrared telescope launching in September 2026. And we want to use this telescope to find superluminous supernovae at high redshifts, at high distances from us. And in order to do that, we need good models of how they look, which is here, what we produced. And now we can use these models to predict what they would look like at different redshifts in this survey. so that we can optimize the parameters of this survey to maximize the discovery of these objects. And why do I want to find superluminous supernovae at high redshifts? So this is a plot of the star formation rate as a function of redshift. And core collapse supernovae, the regular ones, the ones that are like dim and produce very active decay, seem to track this star formation rate, but then they start to get really noisy and not that useful. But superluminous supernovae are much brighter, and they can be seen out to much further redshifts. So if we can actually find a population of them, we can start to track the star formation rate as a function of redshift for this population much further than we could with ground-based telescopes or with regular core collapse supernovae. This is my second to last slide. What about the future? The Vera C Rubin Observatory Legacy Survey of Space and Time is a telescope being built in Chile, right? I'm sure many of you have heard about it. But this telescope is not going to discover 1,000 supernovae a month. This is going to discover 100,000 supernovae every single month. It's going to increase our discovery rate by 100-fold. We are already in the era of big data, and this is going to increase it by 2 orders of magnitude. I just heard this week that they're supposed to commence the actual survey no later than December 31st this year. So we should be getting alerts and data and actual supernova detections next year. But the telescope is built, it is in operation, it's being commissioned, the data's coming. I have modified Fleet to work with this data, but that is still being tested and in development. Because to go the machine learning route, Fleet is trained on existing telescopes, namely ZTF. And if we want to use it on data from LSST, we're going to need some domain adaptation techniques to make sure that the data trained on one telescope will work with data from a different telescope, which is something we need to figure out. But I'm going to leave you with one question, because if we're increasing the transient discovery rate by 2 orders of magnitude, we are no longer in the case of we can only follow up 10% of objects. It means that out of every 1,000 transients that happens, we can only follow up and study one of them. Which one do we pick? Thank you.
Any questions for Sebastian? I'll take one in the room and then one online.
Okay.
Very cool. I have a very naive question.
Yeah.
So superluminous supernovae plots where you looked at purity and completeness.
Yes.
What was the reference line?
Oh, which reference line?
What is so the star is Fleet, right?
Okay. The star is the 50% threshold. So that is the point where we say, like, if it's higher than 50% probability, we say that that's like more likely to be a superluminous supernova than anything else.
I see. And then the next slide is a comparison with Fleet.
Yeah. So it's all Fleet, but it's for different thresholds, right? So I can say I'm going to follow up everything that Fleet says higher than 30% probability. My purity would be pretty low. If I say higher than 50% probability, my purity is about 50%. I could just be extremely aggressive and say I'm only going to follow up things that Fleet says are 80% likely to be superluminous supernovae, and my probability would be around 80%, but then I would only find like 1 every 6 months. Yeah, but it's all Fleet.
There's a question online from Miriam. Miriam, unmute yourself.
Hey, hi. Hi, Sebastian. Thank you so much for this wonderful talk. So I had a follow-up question about the host galaxy, right? So just to make sure I understand, right? So you do request the detection of a host galaxy, is that correct? Because that might bias you against kind of more low luminosity galaxies.
I don't actually.
Oh, you don't? Okay.
No.
Okay.
If there is a galaxy in the field with a PCC less than 5%, then I use it. And if I don't, then I assume the object is hostless and assume the magnitude limit of pan-stars as the magnitude of the galaxy.
Oh, okay. So just assume, and then you still do it because the light curve itself is very telling, right? I mean, there's no star that could give such a broad light curve. Okay, and then I'll ask you some questions online because offline because I think there are other questions. Thanks.
Yeah.
And there's a question from NRAO. Ryan, do you want to unmute and ask the question? You're muted. Okay, there's no muted.
Yeah, go ahead. Can you hear us?
Oh. Yeah, I hear you.
Okay, thanks, Sebastian. So I just want to know, when you get your 21 candidates, you then go and confirm them first, before you say, and then do your science, and then do they feed back into the model again, the training set, as you accumulate the training set?
Yes, I retrain it about once a year. It's not with every single object, but like every year we might collect like 15, 20 more objects, and I'll add them in and then retrain. But yeah.
And they are confirmed. How do you confirm them spectroscopically?
Yes. Yeah, they're all, yeah. And I'll also add objects that other people from around the world discovered, which is particularly helpful because the objects that I discover were selected by my algorithm. So it doesn't add as much as an object that my algorithm did not detect. So adding that in, it turns out to be more helpful. But yeah,
Great,
we do add those in.
Can I ask a follow on?
Oh, sure.
Do you anticipate a change in the strategy for how you classify these and monitor the model with like the flood of Rubin data? Or do you think this approach is, yeah,
yes and no, because we're going to get a lot more data, which seems scary and like makes you think that we're going to be just flooded with data. But our spectroscopic resources, they are still limited by the same magnitude, right? We're still not going to be able to follow up the thousands and thousands of objects from Rubin. We're still going to be limited to only follow up the brightest ones. So I think our strategy is not going to change that much, but instead we're just going to get exquisite data on nearby objects and still just be following up these nearby objects the same way we've been doing.
thanks.
No worries.
Question.
Is that the answer to your final question? You're gonna pick the biggest ones?
Yeah, I'm going to pick.
Another question?
Yes.
Yeah, there are no plannings for just a big telescope for follow-up spectroscopy.
GMT. Yes.
Yeah.
Yeah, like there's more, but yeah, GMT is definitely, as UT Astronomy, I have to say, GMT.
One last question to Miriam.
Hey, so just a follow-up. So you mentioned you found 21 out of the 50.
Yes.
Right. And so would you mind commenting on what the others, did you miss the other ones, or were there data that you didn't have access to, proprietary from other surveys?
So some of them, it's a very small fraction that we wouldn't have found otherwise, right? A lot of them, we didn't find them, but we could have if we had had the telescope time or if it wasn't cloudy at night, etc.
Mm-hmm.
A few of them, for example, if they happen in relatively bright galaxies, Fleet is pretty biased against those, right? So there were a couple that happened in pretty big, bright, massive galaxies. Fleet said, that's not a superluminous supernova. We moved on. Turned out it was. So that's probably our biggest failure mode right now.
Okay, thanks.
Yeah.
All right, let's thank Sebastian again.